Let's talk about the special case where we have an invertible linear transformation that's a matrix transformation. So let's let T be a transformation from Rn to Rm. Okay, so it's a linear transformation. Because it's going from Rn to Rm, it's a matrix transformation. So it has a standard matrix M. Okay? Now, just to be clear, not every linear transformation is invertible, just like not every matrix is invertible. But transformation T is invertible if and only if matrix M is invertible. Now, the kind of inverse we're talking about is different in these two cases. Here, when we say T is invertible, we mean a functional inverse. When we say M is invertible, we mean a matrix multiplication inverse. Okay? But they are related, and that's what this theorem is saying. If S is the inverse of T, then S is a matrix transformation, and the standard matrix of the transformation is M inverse. Okay? The inverse of the standard matrix of transformation T. And finally, M and N would have to be equal in order for this to hold. Okay? So let's sketch out a proof. Okay? So first off, we know that T from Rn to Rm, we know that that is a matrix transformation, right? So let observe T of x is equal to M times x. That's what it means to be a matrix transformation. Also, if S is the inverse of T, then S is going to map Rm to Rn, right? T takes Rn to Rm, S takes it right back. So we know from what we've already talked about that the inverse of a linear transformation is also a linear transformation. And since S is a linear transformation going from Rm to Rn, S is a matrix transformation. With standard matrix, well, actually, let's put it this way. Let the standard matrix of S equal to, let's call it matrix N. Now, what I want to show is that this matrix M, the N that I just defined, is actually the inverse of matrix M. And I'm just realizing N may not be such a great matrix here because it sounds a lot like M. Let's just call it matrix A. So the standard matrix of S is matrix A. So I want to show matrix A is actually the inverse of matrix M. Okay? Then S of x is equal to matrix A times x. Right? That's what it means for A to be the standard matrix of linear transformation S. But S of T of x equals A of M times vector x, which is equal to AM times x. Okay, now this holds for which, and this just equals x because S and T are inverses, right? Now this holds for every possible vector x. since this is true for all x, it follows that A times M must be the identity matrix. Okay. Similarly, T times S of x is equal to M times A of x, which equals MA times x. And again, T and S are inverse transformations, so that's just vector x again. Since this is true for all x, it must be that the product of M times A is, again, the identity matrix. So when I say it's true for all x, I didn't pick a specific x, right? This statement works for all x. Okay. In particular, this equality at the very end here is true for all x. This equality at the very end here is true for all x. Now, if A times M wasn't the identity matrix, there'd be some x I could pick so that this wouldn't be true. A times N would do something to actually change the vector. The only vector that leaves all the only matrix that leaves all vectors unchanged is the identity matrix. Same thing here. The only matrix that leaves all vectors unchanged when I multiply is the identity matrix. So A times M is the identity matrix, M times A is the identity matrix. That's exactly what the definition of matrix inverses are, that the product of AM and the product of MA are both the identity matrix. Thus, A is equal to M inverse. Okay, we've proven that because these two properties are what it means to be an inverse matrix. I can multiply them on either AM or MA. If I get the identity matrix both ways, they are inverses of each other. Okay. And essentially we are done. Okay. We have showed that, hey, if T is an invertible transformation, then its standard matrix M is also invertible. Okay. The inverse transformation of T has as its standard matrix the inverse of matrix M. Okay. Finally, M equals N because in order for two matrices to be inverses, they have to be square. Remember the standard matrix M of this transformation, it would have M rows and N columns. But if it's a square matrix, that means M and N actually have to be equal. Since matrix M is invertible, it must be square. Only square matrices can be invertible. Meaning M equals N. Okay? All right, so let's put this into practice. Let's do an example. Let's take a transformation T from R2 to R2. We have the linear transformation T of xy is equal to 9x plus 34y, negative 4x minus 15y. Okay? We want to find the inverse of T. So if this is a linear transformation from R2 to R2, and it says it is, the problem says it is, then T is a matrix transformation, right? If we can find the standard matrix associated with transformation T, then the inverse of that matrix will give me the inverse transformation of transformation T. Okay? In other words, if T of x is equal to mx, then the inverse transformation of T is equal to the matrix inverse of matrix M times x. So my strategy here is to find the standard matrix of transformation T, invert that matrix, which we have learned how to do, and that will give me the inverse transformation. Okay, so how do I find the standard matrix of a linear transformation? Well, remember, the standard matrix of a linear transformation is just the transformation of the vectors in its standard basis. Okay, so this will be the standard matrix of T. Okay, so if I take the transformation of I, which would just be 1, 0, if I plug 1 in for x and y and 0 in for y, I can see that the transformation would be, let's see, first row, 9 times 1 plus 34 times 0 would be 9. And negative 4 times 1 minus 15 times 0 would be negative 4. Okay? And if I plug in j is the vector 0, 1 in R2. So if I plug in 0, 1, so 0 for x, 1 for y, my first component, I get 9 times 0 plus 34 times 1. That's just going to be 34. My second component, negative 4 times 0 minus 15 times 1. That's going to be negative 15. Okay, so that's going to be the standard matrix of T. So that means that the transformation T on a vector x, so let's be a little more specific here, on a vector xy is equal to our standard matrix, 9, 34, negative 4, negative 15, times xy. And actually, if you look at it, that should be pretty obvious once you see it, right? Row 1, column 1, I just multiply those two. I'll get 9x plus 34y, 9x plus 34y, okay? Row 2, column 1, if I take the dot product of those two, I'm going to get negative 4x plus negative 15y. Indeed, I get negative 4x minus 15y. Okay? So we do have our standard matrix here. Now, in order to find the inverse, we want to find the inverse matrix of our standard matrix M. I'm going to want to find the inverse of this matrix. Remember, the strategy for doing this is I take the matrix I want the inverse of, and I augment it with the identity matrix. In this case, the 2 by 2 identity is 1, 0, 0, 1. I am going to find the reduced row echelon form of this until this is the identity matrix. And then over here will be the inverse of M. Okay. If I can't get this left-hand side of the augmented matrix to be the identity matrix, then the matrix doesn't actually have an inverse. And in that case, the transformation, it would not be possible to have an inverse transformation because it doesn't exist. We can't find it because it doesn't exist. Okay, so if it exists, we better get the identity matrix over here after we row reduce, after we find the reduced row echelon form. Whatever is left on the right side of the augmented matrix is the inverse that I'm looking for. Okay, we're going to have the computer do the heavy lifting for us. All right, so I want to find the reduced row echelon form of this matrix here. Okay, let's put it in. We'll call it matrix A, 9, 9, 34, 1, 0, negative 4, negative 15, 0, 1. And there we have our matrix in reduced row echelon form. So let's plug that in here. We get 1, 0, negative 15, negative 34, 0, 1, 4, 9. Okay, so we do get the identity matrix on the left side of our augmented matrix, which means this over here, that is our inverse. That is our matrix inverse. Okay, so the inverse transformation of T is just going to be the inverse matrix times the vector. So that's going to be negative 15, negative 34, 4, 9 times the input vector with components x, y. Okay, and if we actually do the matrix vector multiplication, we see we'll get negative 15x minus 34y in the first component, 4x plus 9y in the second component. So that is the inverse transformation of our original transformation T.